Okay guys, so today we are going to practice graphing polynomial equations using zeros or roots, and this piggybacks on what we did last class. So last class we wrote the equations given roots. Now I'm going to give it in standard form, okay, and we're going to factor. So you have to be able to factor today. So you can see here on the first part of the notes 1, 2, and 3. I just want to remind you about the factoring. You should always take out a GCF first, and remember GCF is highest number that'll go into everything and lowest variable. So for number 1 here, I'm going to take out and divide by 4 because 4 goes into them, but you can see they all have an x, so I'm going to take 4x out, meaning I'm going to divide by 4x. So 4x, and then put that on the outside. That's going to make x squared plus 2x minus 8. And then from there, remember you're looking for two numbers that we could do the t-chart, but honestly, since now that there's a 1 in front of the x squared, I'm going to look for two numbers that add to this and multiply to that, which are positive 4 and negative 2. And there's my answer. You just put your GCF in front, and in fully factored form, we went from standard to factored form, and that's going to help us find the zeros, because remember when we solve, we set them equal to 0. So you have to be able to factor to go from standard form into intercept form to graph. Let's do number 2. There's a 1 here, so 1, 3, and 18, nothing there other than 1, but x squared is the lowest amount of x's that they all could fit in. So I'm going to divide everything by x squared. So when I divide it out, it comes on the outside, and then left inside have to be 3 terms. If there were 4 in the problem, I took out 2. There's 2 here left. Minus 3x minus 18. Okay, and you can always check your work by distributive property. Then from here, two numbers that add to negative 3 and multiply to negative 18 are negative 6 and positive 3. And again, you bring your GCF right in front. So you've got to be able to factor, guys, okay? It's really no exception this time. And the last one here, highest number that'll go into 4, 14, and 6 is 2. And you can see here they all have at least one x. You always want to take out the lowest x so that they have in common. So I'm going to divide by 2x. When I divide by 2x, that's going to make, that goes on the outside, remember, and that'll make 2x squared plus 7x plus 3. Then I'm going to try, now in this case I have to do the t-chart just for what was in the parentheses left over here because the first number is not a 1. So numbers that multiply to 2, 1 times 2, numbers that multiply to 3, 3 and 1, and you can see 2 times 3 is 6, 1 times 1 is 1. For them to add to, always adds to the middle, to a 7, they just both have to be positive. And I put the x there and it goes across. So in fully factored form, I have 1x plus 3, and I have 2x plus 1. And then you just drop the GCF and put it in front. So we're going to be using factoring today to rewrite the polynomial functions into intercept form, and then from there we're going to graph it. So we're going to really start putting all the pieces together between the end behavior that we've been practicing, the factoring that we've been working on, okay, and then the solving that we've been working on. It really comes together. So let's get started. Graphing polynomials with a degree higher than 2. And I said higher than 2 because that's what we did in quadratic. So let's take a look. First of all, what type of function is it? Well, you could see here the degree, okay, degree equals 3. So for that reason, it is a cubic function, okay? And then how many zeros should it have? Since the degree is 3, okay, it should have 3 zeros because the degree equals 3. Whatever the degree is, guys, that's how many zeros there are, or roots, or x-intercepts. Remember, they're all the same term, so that's what we're talking about. How many times it should hit the x-axis, okay? Then here, what is the end behavior and how do you know? Draw your ends of your graph accordingly. Okay, so the end behavior, what we've been talking about, we know its degree is 3. so that makes it odd. And looking in front of that, the leading coefficient is a positive 1, so it's positive. So the end behavior, let's draw the arrows on the graph. Remember, you have to know this, odd positive is going to look like that. So on the left side of the graph, y is going to negative infinity down, and on the right side of the graph, y is going up. That's why you have to know overall, guys, what the end behavior is, so you know where to start. Now we're going to take our standard form and go to factored form. So I'm going to just rewrite the problem here. We're going to do exactly what we did at the beginning. So GCF first. So I'm going to take out x. That's going to leave me with x squared minus 7x plus 12. And remember, when I say take out, I mean I'm dividing everything. The GCF was 1 as a number, but they all have, you always have to take out the lowest letter, and then the lowest letter was x to the first. Then two numbers that add to negative 7 and multiply to 12, x minus 4, x minus 3, okay? And then you bring your GCF in front. So this, guys, is the factored form equation. Now, what do we do to that? Remember, if we're trying to find the zeros where it hits on the x-axis, the rule is it goes back to solving. You set every factor equal to 0. And that includes any GCF that has a letter in it. So our GCF is a letter. So we're going to do, there's going to be 3 roots here. It had a degree of 3. So we're going to have 3 x-intercepts. I'm going to be setting x equal to 0. So there's one of my x-intercepts. Let's plot that point. I'm going to set x minus 4 equal to 0. So x equals 4. There's another x-intercept. So 1, 2, 3, 4. And then here's the other one. X minus 3 equals 0. X equals 3. 1, 2, 3. So again, you have to factor, then you take the factors, okay, and you set them equal to 0. Part of the solving that we've been doing, that is it. That's how, every time we solved, you found x-intercepts, and now we have them. Now we have to sketch based on the roots. Now, what that means, guys, is each of these was one individual number. So we call these single roots. So all of these, all 3 of these are single roots, which means they only occur once, okay? And that means we're going to go through the graph at these points. So, for instance, I know, okay, it's just a sketch, I have to go through this root, but this is where it gets kind of funky, right? You got to turn around and you have to go through x equals 3. That's an x-intercept. So we're going to go back down, but then again, I have to turn back around because I have to go through x equals 4, and then my end behavior is up here. So I'm just going to turn around and go back up. Now again, this is just a sketch, so I'm not necessarily sure if this curve, this turnaround, should be down here or if it should be up here. I'm not too sure, but it's just a sketch based on roots and the overall behavior. And like we've talked about, look, you can only have a max of 2 turnarounds because it's a degree of 3. And we said on the first day of polynomials, you take the degree of the function minus 1, and that's the maximum amount of turnaround. So we did it pretty much right. 1, 2, and you have all your 3 roots. That is what we're going to be working on. So that is what happens when it's in standard form, and you have to put it in factored form, okay? Now let's look at when it's already in factored form. So turn the page. Okay, when you see these, this is where it gets a little tricky. Okay, imagine if we had to FOIL and multiply everything out. You would have this x, put a little 1 there because it's to the first power, times this x, times this x, times this x. Eventually, all these x's would have to be multiplied. That means eventually you would have x to the 1, 2, 3, 4th power, okay? You would have x to the 4th power, which is a quartic polynomial function. Okay? And again, that's if we went back and did that. We're not going to do that because we want it in factored form. So again, this is already in factored form, intercept form, whatever you want to call it, which makes me smile because that saves me the step of factoring. I don't have to factor anymore. Now, knowing that there's 1, 2, 3, 4 here, 4 factors, it's to the 4th power, there should be 4 zeros. And again, there should be 4 zeros. I know that because that's the rule. The degree of the function, which would be 4 after we multiplied it out, has to be equal to the number of zeros, x-intercepts. So the end behavior, let's take a look. The end behavior, we can clearly see the degree again is going to be 4. So that's an even number. Then, though, you have to take a look at the very leading coefficient of how it's going to be affected eventually, which is right here. This is your LC, guys. So because you can see that LC, the very first number, even if we were to FOIL it out, it's going to keep that first number to be a negative number. So since our LC is -2, we know that our end behavior is down and down. Remember, same when it's even. And you have to start with your end behavior. Now, again, same thing. Find the zeros by setting each factor equal to 0. I'm going to do that down here. We already have it in factored form. There are 4 factors. Factor 1, 2, 3, 4. So we're just going to set them each equal to 0 and find the numbers. So factor number 1, -2x equals 0. Factor number 2, x minus 2 equals 0. Factor number 3, x plus 3 equals 0. And factor number 4, x plus 5 equals 0. So from there, solve each of these factors. Again, they just came from up here. Let's solve them. So this one has to be x equals 0. Okay, that has to be the case because -2 times 0 makes 0. Here, if I add the 2 over, I get x equals 2. Subtract the 3, x equals -3. And subtract the 5, x equals -5. So you could see all we did again was, at least we skipped the step of having a factor. All we did was take the factors, set them equal to 0, and solve. So now let's plot them where they be. So x equals 0 is here. X equals 2 is about here. X equals -3, so 1, 2, 3 is about here. And -5, 1, 2, 3, 4, 5. Okay? So again, you have about where they're going to go. All right? We know the end behavior, so if I really wanted, I could like squeeze my arrow over here more. It's not a big deal, just to match up. Each of these, you could see, only shows up once. So again, we call these single roots, meaning at each of these spots, we have to just go straight through the point. Okay, no weird anything, just straight through the point. So that means I'm going to start here, because we start down at the bottom with even, negative. I'm going to go up. And again, I have to turn around because I have to go through this point. Then I have to turn around because I have to go through that point. Then I have to turn around because I have to go through that point. So that is an approximate sketch of the graph. All we're using to sketch is based on the roots and the end behavior overall. Again, you could see 1, 2, 3 turnarounds. 3 turnarounds there because it's a degree of 4, so you can't have a turnaround that's higher than that, okay, or equal to that. So just an idea of the sketches. So we're going to do 2 more. Again, let's take a look at the next page where I like it because it's already in factored form. Okay, so you can take a look here. This is already in factored form. The nice thing about factored form is, again, you skip the step of factoring, but even better so, look, they did the hardest work for us. You could see these exponents. This is where, again, they're rewriting something much smaller than what it came out to be. So what I'm saying is, this is the same as writing it as 2x, x minus 2, x minus 2, x plus 5, x plus 5, x plus 5, x minus 4. Now, how are they the same? Because of the exponents, guys. Remember, when you square something, you're multiplying it by itself. So I have it right there. When you raise something to the third power, you multiply it by itself 3 times. And there. So basically, this must have been a huge polynomial function that they had to do a lot for to get it to here. But they just condensed it and wrote it in this form for us. Now, what's important is what type of function is it, and how many zeros should it have? How do we know? Well, first of all, if you could see, if we go back to this form, it means if we were to FOIL this out, guys, we would have 1, 2, 3, 4, 5, 6, 7 x's. So x to the 7th power, which doesn't have a particular name to it, okay? But you have to keep that in mind. So when you're in factored form, you got to kind of count up the powers of what would be if you were to FOIL or multiply it out. Personally, I like to do this instead of writing this large expression every time. I just count these exponents. 1 plus 2 plus 3, and then I count the 1 that's here. They're never going to put the ones, guys, but just it's there because there's an x. So 1 plus 2 plus 3 is 7, so I know it's going to be x to the 7th. That means how many zeros should it have? It should have 7 zeros. And why? Because the degree will equal the number of zeros. So let's talk about the end behavior. End behavior of the graph, well, you can clearly see the degree is going to end up being 7 if we were to multiply it all out. We're not doing that work. That goes back to standard form. So the degree would be 7, which is odd. And you could see the LC in front, guys, is 2. You can see it right here. Again, it's always that number that's in front, so then that's positive. So from there, on the graph, odd positive means it goes left here and upward. So it's kind of an upward trend through the graph. Now here's again where it gets interesting. We're going to find the zeros by setting each factor equal to 0. So we have, now here's where it's weird. We have 7 zeros, but we only have 1, 2, 3, 4 factors. We'll be talking about that. So let's set each of those factors. 2x equals 0. X minus 2 squared equals 0. Notice, don't drop the exponent. X plus 5 cubed equals 0. X minus 4 equals 0. Now, you don't really have to keep the parentheses here. I just kind of did. Here's the thing. Remember, to solve this, x is going to have to equal 0. That's one of our roots. Okay. Here, we would have to do the square root. The square root of 0 is 0. So it would be x minus 2 equals 0. So x equals 2. That's another root. Here, I would have to do the cube root of each side, like the opposite of doing square root, okay, is to the 2nd power. So 3rd power is cube root. But again, the cube root of 0 is just going to be 0. So then you get x equals negative 5. And then here, I don't have to worry about that. I'm just going to add the 4, and I get x equals 4. Now, this is where it gets interesting, guys, okay? Like we said, there has to be 7 zeros, 7 x-intercepts. We only have 4 numbers. Okay, let's plot these numbers first. So x equals 0 is here. X equals 2 right here. X equals negative 5. So 1, 2, 3, 4, 5 right here. And x equals 4. 1, 2, 3, 4. So you can see now there are 4 zeros here. How do they make up the 7 that should be there because it's a degree of 7? Here's how. At this root, guys, it was raised to the 2nd power. For that reason, we call this, guys, a double root. Any time that it's raised to the 2nd power or 4th power, any type of even root, it's worth that amount. But what you do on the graph is it does a bounce off. And I'm going to show you what that means. Okay? So that's the red flag that you know this root is worth 2 zeros together. And makes sense because if you do the square root property, it's technically supposed to be 2, but, you know, 2 answers, but you can't do that with 0, so it looks like 1, but it's really worth 2. The other thing is here, this factor being to the 3rd power. This is what we're going to call the triple root. It's worth 3 roots altogether. And what you do for the graph at this point, it's kind of like a plateau, it's kind of like a curve through. Some even people call it squiggle. So we're going to just say curve through. Okay? So it's going to be really important at those 2 spots or our end behavior is not going to work. Okay? You have to make sure you can remember that because if not, you're not going to be able to get from arrow to arrow without drawing a line through at a different x-axis. So here's what I mean. So, and then these 2, by the way, only occurred once. They had no exponent with them other than 1. So these 2 are called the single roots, which just means, again, just like the other 2 we've done, you're just going to go straight through them and not worry about a specific way of how to do it. So let's take a look here. Okay, so 1, 2, 3, 4. Okay, -5 is here. -5 is supposed to represent a triple root. So when you come across it, go up to it, and then watch this. You gotta kind of, it looks strange, you gotta kind of do it like a little squiggle through it. Kind of like a little curvy curve through it. Okay, so do that. Then we realize, okay, we have to turn around at some point because we have to go through this x-intercept. That's where x equals 0. So now, do a little turnaround. We don't have to do anything fancy through here because it's a single root. So just go straight through. Now we have to turn around at some point. So look at this. I have to turn around and hit 2. But 2 must be a double root because it was to the 2nd power. So what that means is you're going to go up to 2 and you're going to bounce, which means turn around. Okay, so this again represents a double root. See how it bounces? This little squiggle through, this little curve means it's a triple root. Now, last but not least, I have to turn back around and go straight through, okay, for the single. So these are going to be the big points. Single roots go through. They're only worth 1. Those are my singles, okay? This is my double root. And this is my triple root. All together, when you add up 3 plus 1 plus 2 plus 1, just like we did before, we got a degree of 7. And that is what we want. You're going to get a chance to keep practicing these, okay? But you got to be able to recognize those characteristics. So, last one here for the notes. Turn the page. Let's go over this example where it's multiple choice. So sometimes as well, guys, not only are you going to be expected to produce a sketch, but then you're going to be expected to use your knowledge to pick out, okay, a graph based on what they give you in the equation and based on the roots. So let's take a look here. You can see, let's add up to figure out the degree. 1, 2, 3, 4. Okay, so 1, 2, 3, 4. So this is going to have a degree of 4. And again, I'm counting those because if I were to FOIL and multiply them all out into standard form, I would end up getting x to the 4th power eventually. Then you can look at your LC, which is the number in front. Here, if they don't have a number, it's a positive 1. So my LC is a positive 1. So right away, hopefully with the end behavior stuff, you can know your arrows are supposed to be up and up. So there's no way it can be B because that's down and down, and there's no way it can be C because that's down and down. So hopefully, again, you've got to know your end behavior. Now, after based on the end behavior alone and eliminating choices, now let's find the zeros of each of these factors to determine which one best it would look like. So we have x minus 3 equals 0, x plus 5 equals 0, and x squared plus 4 equals 0. So x equals 3, x equals negative 5, and then, okay, this is where it gets a little weird. Okay, let's solve it. Subtract the 4. We're going to use square root property. So x squared equals -4, and then we're going to do the square root of it. Well, guys, we've talked about this a bazillion times. You cannot do the square root of a negative number, so this is actually going to be plus or minus 2i. These are imaginary roots. Now remember, imaginary roots is where it does not touch the x-axis. So let's kind of look and see between these two graphs. Okay, so this, well, I already see an issue. Look, this touches 1, 2, 3, 4 times. This has 4 real roots, zeros, whatever you want to call them. We already know we have 2 imaginary roots and only 2 real roots. So there's no way it can be A. So how is it D? Well, this could represent where x equals -5, that's single root. This could represent where x equals 3. So where would the imaginary 2 come from? Right here. Imaginary roots, guys, are going to come from where the graph turned down before hitting the x-axis. So again, imaginary roots come at the spot before it hits the x-axis. And we're going to keep practicing that some more. So you have 5 practice problems, that look like what we just did. 2 where you have to factor, 2 where they are in factored form, okay? And then give some time on those. We'll set the timer, and then I'm going to have the answers for you via video in hopes for you to understand. Okay? Try your best.